All right, so we're going to continue our discussion of these Lewis structures, picking up where we left off last time, and we're going to introduce this concept of formal charge here, okay? So the last structure that we did was this, what's called a cyanide ion here, our carbon-nitrogen with a net -1 charge. And we talked about how we have to factor that -1 charge in when we calculate our number of electrons. We would do the number of valence electrons, the number for carbon, plus the number for nitrogen, and plus that extra one that we get from that net negative charge. So that's how we got a total of 10 valence electrons for this structure here, which we then turned into this Lewis structure. Okay, so it turns out that that net negative charge, that -1 charge, lives on a specific atom in this structure. And we can figure out which atom that is by calculating what's called the formal charge on each of these atoms. Okay, so our formal charge is equal to the number of lone pair electrons plus 1/2 of the number of bonding electrons, or covalent bonds rather, okay, if we sum up all that, we're going to subtract it from the number of valence electrons that that atom has when it's all by itself. So valence electrons minus the sum of the electrons that we see in our Lewis dot structure, the number of lone pair electrons, but then only half of the bonding covalent bonds in our molecule. Okay, so basically when we look at our molecule, we're going to count all lone pair electrons. About an atom. But we're only going to count half of the bonding electrons. Okay? So let's take a look at this structure here, and we're going to do these formal charge calculations for both of these atoms in this structure. All right, we started with our formula. Now we got to our Lewis structure, and now we're going to calculate our formal charge for each one of these atoms. Okay? So I'm going to do this calculation. I'm going to abbreviate formal charge as FC. And we're going to focus first on carbon. So first I need the number of valence electrons that carbon has before I make my structure here, right? This is what we get just by looking at the periodic table based on where carbon lives on the periodic table. How many valence electrons does a carbon atom start out with? 4. And now I'm going to subtract the number of lone pair electrons plus half the number of those covalent bonding electrons. Okay, and actually, let me be good. Covalent bond electrons. All right, so the way that sort of I visualize this here is I'm going to draw a circle around that particular atom, and I'm going to count all the electrons that are in that circle. So I count all of these lone pair electrons, 1, 2, but I'm only going to count half of the electrons in each covalent bond. Each covalent bond is a pair of electrons. I'm only going to count 1, so 3, 4, 5. That's how I'm going to calculate my formal charge on this carbon atom, the number of valence electrons that carbon has before it makes its compound, and then how many electrons we see in our circle here in our Lewis structure. So if I subtract my 4 minus 5, I see that my carbon atom has that formal charge of -1. So in this structure here, the net charge on this ion is -1. Where does that -1 charge live? It lives on that carbon atom. We can continue. We're going to do our formal charge calculation for nitrogen. So let's just say this one's for carbon. We're going to do another one for nitrogen. Okay. Let me get rid of my little markings here. All right, so again, I'm going to look at the periodic table, figure out how many valence electrons the nitrogen atom has. Nitrogen, based on where it lives on the periodic table, has 5. And now I'm going to draw a circle around my nitrogen atom, and I'm going to count how many electrons I have in here, where I count all of my lone pair electrons, 1, 2, but then only half of these covalent bonding electrons. So each of these covalent bonds, I'm only going to count 1 electron from. So that gives me a total of 5 minus 5. And so the formal charge on this nitrogen is 0. Right? So again, we can figure out where the charge in our ion lives based on these formal charge calculations. Turns out that in this molecule here, it's my carbon atom that has that negative charge. The nitrogen has a formal charge of 0. All right, so let's do another one here. I want y'all to do this one from scratch here. First, I'm going to give you this formula. SH with a -1 charge. And you need to draw me the Lewis structure of this ion right here. All right, so if I total it up here, I would have 6 electrons from my sulfur, plus the 1 valence electron from my hydrogen, plus this extra 1 from my net charge of -1. Remember, a negative charge means you have an extra electron. So this brings me a total of 8 valence electrons. I'm going to put down my central atom here, which should be my sulfur, because hydrogen's never the central atom. I'm going to decorate it with that hydrogen and connect with a single bond. I got to deduct from my total here. So now I have 6 electrons left over. First, we're going to make our constituent atom happy, but hydrogen only wants that 1 bond. So I'm done there. Whoops. So where does the rest of these 6 electrons go? On that sulfur. Right, so 1, 2, 3, 4, 5, 6. And now this ion right here has this net charge of -1. So based on what we did, I want everybody to take a second and see if you can't figure out where that net charge lives. Calculate the formal charge on each one of these elements, each one of these atoms. right, sulfur, according to my periodic table, has 6 valence electrons. If I draw a little circle around sulfur in my molecule, how many electrons do I see in that circle? All right, so I'm going to count all of my lone pair electrons, 1, 2, 3, 4, 5, 6, and half of every covalent bond, so just 1 electron there brings me to 7. Oops. So my sulfur has a formal charge of -1 in this molecule. Okay, we can do the same thing, but for our hydrogen. Hydrogen has 1 valence electron. If I draw my circle around my hydrogen atom in this molecule here, how many electrons are in that circle? Just 1, right? So we only count half of every covalent bond. So 1 minus 1 gives me a formal charge of 0. All right, so again, what we can establish is in this ion, SH with a -1 charge, where does that -1 charge live? It lives on that sulfur atom. Okay, and this is especially important when you go on to, say, organic chemistry and you start talking about the reactions of these molecules. That's a little bit more advanced than what we're going to be doing here, but it turns out that when you start making and breaking covalent bonds and predicting the products of these reactions, where those charges live is in large part what dictates what those products are, right? So we're kind of learning this skill here that you're going to build off of in future courses, calculating the formal charge of these atoms. All right, so our formula we laid out for calculating formal charge, again, I kind of think it's easier to just do it visually by circling the atoms, all right? A few more important notes about formal charges here. Okay, ions, molecules that have a net charge, will always have at least 1 atom with a formal charge. Okay, so if we have ions like we had here, we're always going to have at least 1 atom in that structure that has that charge, that has a formal charge associated with it. Okay? For neutral compounds, all right? For neutral compounds, our formal charges must sum to 0. Okay, so there may be some Lewis structures where we have a neutral molecule, but then when we go in and we start calculating formal charges, we see that we have atoms with formal charges. Well, they better sum up to 0, meaning if I have an atom with a formal charge of +1, I must also have an atom with a formal charge of -1. They all got to sum to the net charge on that molecule, which would be 0 for a neutral compound. All right? The most stable Lewis structure, meaning the best one, has no atoms with formal charges. All right, so sometimes you can draw a Lewis structure one of 2 ways, but in one structure, your molecule has a bunch of formal charge. In the other one, all of your atoms have a formal charge of 0. The most stable form of any molecule is when all atoms have a formal charge of 0. Sometimes it's not possible to draw one that way, all right? But if we got 2 options, we're going to pick the one where our formal charge on all atoms is 0. So let's do a simple example here. A very important molecule in this day and age, carbon dioxide. All right, I want everybody to get me the Lewis structure of carbon dioxide here. All right, so I get to this point here. I totaled up my amount of valence electrons that I had to work with. I put my central atom, carbon, in the middle and decorated it with the oxygens on the outside and drew single bonds. That took up 4 of my electrons, so I had 12 left over. What I'm going to do first with those leftover electrons is make sure that the outside is happy. So go around and make sure that my oxygens have a complete octet. And now I'm down to 0 electrons here. All right, so we're not done yet. Why? Looking at this structure, what's wrong with it? Carbon's not happy, all right? Your first concern is making sure that every atom has a complete octet. That's why they form bonds to begin with, okay? So we're going to have to take a pair of electrons from one of those constituent atoms, that's a lone pair, and bring it down here to make it a bonding pair of electrons. So now I have this carbon-oxygen double bond. So now I'm done. No, my carbon's still not happy. My carbon still doesn't have a complete octet. It's only got 6 electrons. All right, but from here, we kind of have 2 options. All right, let me move this to, I have more space. I could either take a pair of electrons from that same oxygen atom and bring it down, making a carbon-oxygen triple bond on one side and a carbon-oxygen single bond on the other side. Or I could jump to the other oxygen. I could take a pair of electrons from there and bring that down, giving me carbon-oxygen double bond on both sides of this molecule. Okay? Now, from an octet rule standpoint, both of these structures are equivalent. My oxygens have a complete octet, my carbons have a complete octet, so they both seem like they'd be legit based on what we learned last class about our octet rule. All right? So, how are we going to break this tie here? Now we have to factor in what we just learned about formal charges. One of these structures, every single atom in that structure has a formal charge of 0. And in the other one, we have some formal charges on our atoms, right? And again, the most stable structure is always going to be when every atom has a formal charge of 0. So let's see if we can't figure out which one of these is going to be the preferable structure here. All right? So let's start over here with our symmetric one. We got these 2 oxygens are the same, so if we calculate our formal charge on one of them, we can equate it to the other one as well. Oxygen has a formal charge, has how many valence electrons according to the periodic table? 6. And so we're going to subtract what we see in our circle here. These 1, 2, 3, 4, 5, 6 electrons. All right, so in this structure here, my oxygens have a formal charge of 0. I can do the same thing for my carbon atom. Calculate the formal charge of carbon. Carbon has 4 valence electrons. If I draw my circle here, I have 1, 2, 3, 4 electrons in that circle. All right, so again, we have a formal charge of 0. All right, so every atom in this molecule has a formal charge of 0. So this is going to be the correct structure for carbon dioxide. This is the most stable structure here with all of my atoms having a formal charge of 0. All right, for the sake of practice, let's go through and calculate our formal charges on this side. I want you all to do this one on your own. right, so if we look at this first oxygen, how many electrons do we have in this circle here? 1, 2, 3, 4, 5. So this oxygen would have a formal charge of +1. All right, if we look at the carbon in the middle, how many electrons do I have in my circle? Right, half of each covalent bond, so 1, 2, 3, 4. So this carbon has 4 electrons, so the carbon has a formal charge of 0. And what about my oxygen on this side? What's the formal charge? -1. We have 6 valence electrons for oxygen. In my circle, we have 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 gives us a formal charge of -1. So if we look at these two structures here, we have one where every atom has a formal charge of 0. And then we have another where one oxygen has a formal charge of +1. The other one has a formal charge of -1. Again, the most stable structure is going to be the one where all atoms have a formal charge of 0. So if we have this sort of tie here where according to our octet rule, both of these work perfectly, we're going to break that tie by calculating these formal charges. Okay? So again, our most stable Lewis structure has no atoms with formal charges. Okay? If it's impossible to draw a Lewis structure with no formal charges, all right, we want that negative formal charge on the most electronegative atom. And the positive formal charge on the least electronegative atom. But we can also say except for hydrogen, because it's too tiny. All right, so remember that electronegativity. This is an atom's ability or an element's ability to pull electron density onto itself. The more electronegative atoms are better at pulling electron density, meaning that they're going to tend to have the negative charge in your structure compared to the less electronegative. They're going to lose that tug-of-war battle and tend to have the positive formal charge. All right. Cool. So we'll practice these formal charge calculations a little bit more. We're going to introduce another concept here. All right. And these are called resonance structures. All right. So let's do an example here. NO2 with a -1 charge. All right, so I'm gonna calculate my total number of electrons here. I got 18 to work with. I'm gonna put down that central atom between nitrogen and oxygen. Which one is the less electronegative element? Nitrogen. It's further away from fluorine, right? So that's the one that goes in the middle. I'm gonna decorate it with my oxygens. I'm gonna draw in those single bonds. For each bond, I need to subtract 2 electrons from my total, so that's a total of 4. So that takes me down to 14. The first thing I'm going to do with those leftover electrons is make everybody on the outside happy, make my constituent atoms happy. 1, 2, 3, 4, 5, 6. Jump to the other side. 1, 2, 3, 4, 5, 6. So then I put down a total of 12. Now everybody's on the outside. Now everybody on the outside is happy, but I still have these 2 left over. Anything left over goes in the middle, on the central atom, right? So this last 2 electrons here are going to go on that central nitrogen. So now I'm done putting down electrons. I got all my electrons on the board. So now I have to look at my structure and ask myself, are we done here? What's wrong with this structure? The nitrogen's not happy, right? The nitrogen does not have a complete octet in this structure. It only has 2, 4, 6 electrons in its octet. All right? But now we're left with this interesting problem. Let me clear some space here. Okay? We have these 2 oxygens, one on either side. We can either take a lone pair from the one on the left here and make a double bond with our nitrogen. Or we can take a lone pair from the oxygen on the right-hand side and bring that down to make a double bond. Oops. So looking at these 2 structures here, let's first ask ourselves, does everybody have a complete octet? Did I draw a legitimate Lewis structure here in terms of following my octet rule? Right, my oxygens, I got this, in both structures I have a double bonded oxygen with 2 lone pairs. So that's 2, 4, 6, 8. 2, 4, 6, 8. All right, I have my nitrogen in the middle that has 2, 4, 6, 8. Same over here, 2, 4, 6, 8. And then I have these single bonded oxygens with 3 lone pairs, 2, 4, 6, 8, 2, 4, 6, 8. So everybody's happy in terms of our octet rule. Okay? Let's calculate formal charges here. Okay, based on what we just discussed, everybody take a second and calculate formal charges. All right, I want you to do it on this left-hand structure, and I'm going to do it on the right-hand structure for us. All right, so if we look at this first oxygen, my formal charge calculation is the number of electrons oxygen has in its valence minus how many are in my little bubble here. 1, 2, 3, 4, 5, 6. So this particular oxygen has a formal charge of 0. If I go to my nitrogen, my formal charge is the number of valence electrons the nitrogen atom has, 5, minus the number in my bubble, 1, 2, 3, 4, 5. So my nitrogen also has a formal charge of 0. And if I go to my last oxygen, again, oxygen has 6 valence electrons. I'm going to subtract how many are in my structure here in my bubble. 1, 2, 3, 4, 5, 6, 7. So this oxygen has a formal charge of -1. Right? So this atom has a formal charge of 0. This atom has a formal charge of 0. This oxygen has a formal charge of -1. All right, and you can convince yourself that basically we're looking at the mirror image here, but I did go ahead and do these calculations as well. In my other structure, my single bonded oxygen has a formal charge of -1. My nitrogen has a formal charge of 0, and my last oxygen has a formal charge of 0. All right? So in terms of our formal charge calculations, we have 2 equivalent structures here, right? There's no way to draw this structure where every atom has a formal charge of 0 because there's a net charge of -1 on this ion. There's going to have to be some formal charge in that structure. And in both cases, regardless of which oxygen I choose, I'm going to have an oxygen with that formal charge of -1. So this is what we call a resonance structure here. What do we have to do? Which one do we pick? The correct answer is both of them. Okay? If you have this tie here, these 2 equivalent structures, you have to include both of them. And what we would do is we would draw them both and we would separate them by a double-headed arrow, what we call a resonance arrow. All right, and we're going to see our polyatomic ions are notorious for having these multiple resonance structures. Okay, so for resonance structures here, if we can draw multiple equivalent Lewis structures, we must include them all. Separated by that resonance arrows. All right, so let me just kind of clean this up away from our scratch work here. If I asked you for the resonance structure of NO2 with a -1 charge, your Lewis structure is not just one structure, but 2. All right? Okay, to finish this off here, our convention is to put these brackets around each structure with the net charge on the outside. All right, again, the Lewis structure is really considered to be both of these here. And these are what we would call, in fancy chemistry speak, resonance contributors. So your Lewis structure for our polyatomic ion is really going to be multiple structures, multiple resonance contributors to actually get the full Lewis structure of your ion, of your polyatomic ion. All right, so given what we just learned here, let's see if we can do the carbonate ion, CO3 with a -2 charge. Everybody take a second and see if you can't give me the structure of the carbonate ion. Again, one of our polyatomic ions. So we're going to have multiple Lewis structures here. Oops. How many total valence electrons do we have in this molecule? All right, so we have a carbon that has 4 valence electrons, plus our 3 oxygens. Oxygen has 6, so the total there would be 18 from that, plus the 2 from my net charge. My net charge tells me there are 2 extra electrons in this ion. So that brings me up to a total of 24 valence electrons. We're going to put our carbon atom in the middle, and we're going to decorate it with these oxygens. Okay, as we said before, the orientation in which you put these oxygens doesn't matter. You can make a little triangle, you can make a little T shape. Really doesn't matter. As long as you have who's bonded to who correctly, the orientation on the page doesn't matter. I'm going to space things out a little bit. And now I'm going to draw single bonds, connecting everything. So those 3 single bonds means that I've laid down 6 electrons here. So I have 18 more to go. I'm going to make my oxygens on the outside happy. And that's all of my 18 electrons. I don't have any more. But I can't stop here because my carbon atom in the middle doesn't have that complete octet. But again, we have this situation where which oxygen do I pull from? Do I pull from this one in the bottom left corner? Or this one, the top one? Or this one in the bottom right corner? And the answer is yes, all of the above, right? You have to draw all three of those structures since they're all equivalent. Okay, so our Lewis structure for the carbonate ion would really consist of three resonance contributors, one with a double bond on the left, one with a double bond on the top, and one with a double bond on the right. And to finish this off, we would put it in brackets with that net charge and separate these structures with that resonance arrow, that two-headed arrow. All right, so again, we would need to do all three of these structures to have the correct Lewis structure, all three of these resonance contributors to have the Lewis structure for the carbonate ion. Cool. All right, we'll pick up here next time. All right, later.